Hello everyone and welcome to today's webinar, Lasers, Cameras, and More, Other Sensors Integrated with GNSS for Special Mapping Requirements, brought to you by GPS World Magazine and our sponsor, Laser Technology, Inc. I'm Joelle Harms from North Coast Media, Senior Digital Editor for GPS World, and I'll be your event manager. Before we get started, I want to let you know that today's webinar will be recorded. You are currently in a listen-only mode. A recording of this webinar will be posted to gpsworld.com/webinars and also will be emailed to you tomorrow. At this time, I'd like to acquaint you with the ways you can participate during today's presentation. Please notice the submit button in the lower left-hand corner of your console. If you have a question, type it in the text box at the bottom left and click submit to place your question in queue. We encourage you to ask questions throughout the presentation. We will address these questions at the end of the presentation during the Q&A portion. If you experience any technical difficulties during today's event, you can also use the Q&A box to submit your issue, and Assistant Producer Bethany Chambers or I will personally assist you. GPS World's Twitter feed is placed on the right side of your screen. You can use the hashtag GPSWorldWebinar to submit any questions during today's webinar or to enter into discussions with other attendees. You can learn more about our speakers and our moderator by viewing their photos, bios, email addresses, and Twitter handles located in the upper left-hand corner of your console. And if you're logged in to any of your social media accounts, you can share the webinar's title, description, and URL with your friends or colleagues on popular social media sites. A PDF version of this presentation is available within the resources widget on the left, where you'll also see any links or URLs mentioned during the presentation listed there. So with that, I'd like to turn it over to our moderator, GPS World Publisher and Editor-in-Chief, Alan Cameron.
Thanks very much, Joelle. And welcome to everyone around the world. I see we have attendees from at least 3 continents at my count, perhaps more. I'm Alan Cameron from GPS World, and I'd like first of all to say thank you to our sponsor for today's webinar, Laser Technology. We'll be hearing from Laser Technology midway through the program, telling you about some of their new tools for precise data collection. As most of you know, field data collection and mapping are just exploding, mushrooming everywhere. Turns out that maps are really useful for a lot of things besides what we used to use them for. And with this expanding use in many industries, the demand for accuracy and data richness has really increased. Luckily for us, the technology to obtain it has also been on the rise. And the frontiers for mapping are moving outward and inward, and by inward I mean indoors. Indoor maps are becoming almost as important as outdoor maps for a variety of applications. So with these, and as we know, GPS or GNSS do not work everywhere. They certainly don't work very well at all indoors, and there are plenty of obstructed environments outdoors where they don't work very well. So a lot of positioning challenges for comprehensive mapping, and to meet these challenges, we have available to us a range of other sensors to complement GNSS. Laser rangefinders being prominent among them. There's also inertial measurement units and various kinds of cameras. We have today speaking to you on these topics 3 experts who have lots of hands-on experience using them. First of all, Joakim Rydell from the Swedish Defense Research Agency, who's going to talk to us about some new techniques for indoor mapping. And this has arisen to meet the needs of firefighters and security personnel and others who need to navigate indoors, and their supervisors need to be able to see them on some kind of digital map, often in smoke-obstructed environments in addition to other kinds of instructions. Derrick Reish from Laser Technology is going to talk about the new tools that his company provides for surveyors and GIS professionals and others to augment their GNSS data in obstructed and difficult to reach environments. And Eric Gackstadter contributing editor to GPS World and Geospatial Solutions, is going to talk about a range of techniques and sensors that he has used. We'll fill out the last quarter of the hour with your questions. I'll select from them and pose them to the panel. Right now, let's hear from Joakim, the author of the cover story in the excuse me, in the July issue of GPS World. He's going to tell us about using sensors inside buildings. Joakim, please take it away. And I think we're having a little difficulty hearing Joakim. He's speaking to us from Sweden. I'm hoping that he has not lost his phone connection. If
I'm
we
still
don't
here. Can you hear me now?
Yeah, now we hear you great.
Yeah.
Go ahead.
Great. Perfect. Thank you for the introduction, Alan. I will be talking about what we do at the Swedish Defense Research Agency, or FOI as it's called in Swedish, in the fields of indoor positioning and mapping. And of course, this is not all my work, but things we've done in our positioning group, mainly consisting of me and Erika Bilok, who's the co-author of, well, the paper which is published in GPS World that Alan was talking about, and most other publications from us on these topics. What we do is focus on positioning and mapping in environments where GPS or GNSS systems do not work very well. I mean, if you go indoors, you typically get a GPS connection, you can see satellites, you get a position estimate, but it basically just tells you which building you are in. And most of the time you already know that. You want something more precise. What we do is focused on military use, of course, also on civilian use for first responders, that kind of organizations or people. And we also see that it can be used for robots, either remote controlled or autonomous vehicles. One thing that's very important for both the military and civilian use cases that we address is that these systems are independent of any infrastructure installed in the building. That is, we do not want to do something like you could install in your shopping mall or something, where you put up a lot of beacons and position yourself relative to those, because then you need to be there before and you need to install the beacons and measure their precise locations and so on. You need to be able to go somewhere for the first time ever and still get your position and an overview map showing you where you are approximately. And as I said, position is important, mapping is important, and 3D models is kind of optional, but actually it's most of the time it's easier to get a 3D model and then do a projection to get an overview map than do it the other way around. For positioning in indoor environments, you can imagine any number of different systems, really. Most of the work we do focus on using some kind of imaging sensor, like a visual camera, a typical ordinary camera, or a thermal camera, these emitted heat from different surfaces or objects, or an active laser-based camera where you emit a pulse of laser and you basically measure the time until it's reflected in each pixel. And that way you get an estimate of the distance to whatever you see in each pixel. But you can do it in a whole lot of different ways. You could use foot-mounted inertial navigation systems. You can use the radio systems where you measure distance between different units, or between like each firefighter or soldier and some vehicle that's stationed outside the building, and triangulate your positions that way. And actually what we believe is that you need to use a combination of all these kinds of systems. Because if you just use the camera base, you can always come across some kind of environment where you don't really see anything useful. And if you just use radio based, you come across environments where radio signals don't penetrate walls well enough, and so on and so on. So what you probably need in order to make it really work every time is a combination of several, at least, of these different kinds of systems. But our main focus in our work is the imaging base. And there is one real nice thing about image-based navigation systems, and that is that they can provide mapping information in addition to just the position. Because if you just have, for example, the foot-mounted inertial sensor, it can estimate your position, your velocity, and your orientation, but you do not get a map from it. But if you complement it with some kind of imaging sensor that can see the environment, you can also get the mapping. And I think this was very well illustrated. It was last year, I think, I was traveling to a conference. I was going to talk about exactly this kind of thing. And I was asleep on the plane and woke up. And of course, first thing you wonder when you wake up on an airplane is, are we there yet? So I looked up at the in-flight information system, the one that shows you altitude and distance and time to arrival and so on. And it showed something similar to what you see in this slide. But the aircraft was oriented in the right direction, of course. Sorry about that. It didn't really provide very much information. It was a position, but there was really no map, or at least no useful map. After a few seconds, they zoomed out, and I realized that we were passing across Greenland, and the map actually looked like this. So, but it wasn't there wasn't much information in it. You really need the map in order to interpret a position and to make it useful. And as I mentioned briefly, we work on a number of different systems, or actually prototype systems. They are kind of large and bulky and heavy and so on, but they're meant to be demonstrators of the technology, not the final product. But we work on a number of different systems to test and try out what benefits can you get by using a certain type of sensors compared to something else and so on. So what you see in this slide in the top right corner is a system consisting of two visual cameras, ordinary cameras. They see the same thing you see with your eyes, in a combination with an inertial sensor, the orange thing in the center of the image. So basically, we use the inertial sensor to get an approximate idea about how we move around, and then we track a number of landmarks, corners, or symmetry points, or that kind of thing in the image stream, and use that to correct errors in the inertial navigation. What you see in the bottom left corner is another variation of the system where we replace the visual cameras with thermal cameras that see heat radiation, but we still have two of them. This one is quite a lot larger and bulkier because we need to enclose it in this large box in order to avoid it overheating when we ask firefighters to carry it into a burning building for experiments. So actually, the firefighters usually go in pairs of two, but for our experiments, they needed a third firefighter just to carry the box. And that's, of course, a result of it being a prototype, not a final system. It should be noted, though, that all these sensors can already now be made small enough to mount them in the helmet or on the shoulders or something like that. But because of convenience, really, when we develop this, we want something that's easy to work with, and then we make it quite a lot bigger. We also work on a system where we use an active ranging camera. That's one of these laser-based systems where we use an active illuminator, and we measure the time of flight, really, from that we send out a pulse of light until the light returns, and that way we get quite a good estimate of the distance to everything we see. And of course, getting the distance is the point of having two cameras in the passive systems without laser. So two visual cameras or two thermal cameras. And we also do a little bit of work on integrating these systems with GPS for scenarios where you transition between outdoor and indoor environments. But I won't be talking about that right now. The active ranging camera that we have tried so far is actually the Microsoft Kinect version 2. It's a really good sensor. It costs next to nothing, and it provides very good distance estimates in indoor environments. That is up to a distance of like 5 or 10 meters or something like that. As long as you don't have a lot of sunshine, that kind of makes the laser difficult to see. All of these systems have quite a few things in common algorithmically. So all of them basically perform SLAM, simultaneous localization and mapping, based on an extended Kalman filter, which is quite an old approach, but which actually works quite well, I would say. Partly thanks to us having pairs of cameras or active distance measurements, because it makes the problem much easier. We know how far away the things you're looking at are. So we use the inertial sensor to predict or estimate approximately what happened. How did we accelerate? How did we rotate since the last image frame? And then we try to track corners and symmetry points, as I said, in the video stream to correct the positioning errors that creep into the pure inertial solution. And then, of course, we also feed back these. We estimate the errors in the inertial, the error growth in the inertial system, the biases in the IMU, based on this feedback from the visual or thermal or active ranging systems, so that we can improve the estimates to the next frame and so on. And we process between 10 and 30 frames per second, so we never rely on just inertial for a very long time. And in all these systems, we include a small computer, which is in performance comparable to quite a good laptop. It's on the mobile i7 CPU. And we transmit the positioning and mapping results to tablet computer in real time, so we can see what happens, how we are moving around and how the map is created and so on. And I will provide links to a few demonstration movies where you can see how this interface looks, how it works. The actual mapping is actually quite easy as long as the positioning works well, because again, since we have two cameras or since we have the active camera, we can measure distance, everything we see, or to large parts of what we see at least. And then we know where is walls or objects or whatever we observe relative to our own position. And then we know our own position from the positioning, we know our own orientation. We can take all these points where we see things and transform them to a global coordinate system and just add all the points to large point cloud, which represents the world around us. And then we can look at that from different points of view, and if we observe it from right above, we get the kind of overview map in this slide. And I apologize for the very long and, well, not very easily copied URLs in this slide, but there should be a text document of some kind visible to you. I think it should be on the left-hand side of your screen, where you can copy or perhaps even click this link to get to YouTube videos. So I encourage you to view them to get an idea of how this works. This slide shows an example of an experiment we performed together with the soldiers at the CBRN group in northern Sweden. The CBRN group, excuse me, the CBRN group worked with the nasty stuff like chemical and biological and radioactive agents, and try to find them and isolate them and contain them and so on. And as they do this, moving around in some unknown location, they of course need to know, where am I? How did I get here? How do I get out of here if something goes wrong? And so on. So they are highly interested in this mapping thing. And what you see in the lower left corner here is the map and the trajectory when a soldier moved around this building with our system strapped to his vest. And what you see in the lower right corner is, again, the same thing in white, and the results from a highly accurate reference system, which you need to carry around, do a measurement, takes a few minutes, carry it to a new place, take a new measurement, and then merge these afterwards. Of course, the things we work on, we need to be able to estimate positions and maps when you're moving around quite naturally. So you don't want to place restrictions on how fast you can move or how you should behave while walking around the environment. But as you can see, the white and the black outlines in this figure line up quite well, I would say. So within a room, we will have perhaps a few centimeters of inaccuracy. And because of some drift over time, You can see that we have aligned it to the room in the lower right corner, and you can see that it's not perfectly aligned in the other parts of the building, but it's still quite good, I would say. Good enough to really understand where you are and how you got there. And these are more examples, but here it's from an experiment we performed together with firefighters, smoke divers, again in Sweden. So what you see is pretty much the same thing. The lower right corner is a building. The black outline is from our system. The white outline is from the reference system. And again, they line up quite well. Sorry. It should be said, though, that these results are from the active laser-based system, the Microsoft Kinect. And it penetrates light smoke quite well, but it does not penetrate heavy smoke, like from a house fire or something like that. They need to do something else. And what you basically need to do is use thermal cameras, because they see pretty much right through typical heavy smoke, even if it's very thick. That's because of the wavelength. These cameras observe wavelengths between 8 and 12 micrometers. Ordinary visual light is like half a micrometer, something like that. And the smoke particles in typical fire smoke is about 1 to 2 micrometers, I think. And since the wavelength is much larger than the particle size, we can see pretty much through the smoke. And that's a good thing about these thermal cameras in fire scenarios. These images are from an experiment we performed with other firefighters and smoke divers who carried the system around inside their training facility and produced position and mapping estimate. I will provide a link to a movie showing this a few slides later. And it actually works quite well. We need to sort out a few practicalities with condensation on the lenses and that kind of thing. But from an algorithmic and measurement point of view, it really works quite well. Let's see, next slide, here it is. Yeah, this is just to give you an idea about what the thermal cameras see compared to what visual cameras see. These pictures are taken from the same point of view, although the field of view of the thermal camera to the right is slightly smaller than that of the visual camera to the left. And the colored dots on these images show points of interest that could be used as landmarks, something to track, to keep track of how we move around in the building. And these images show, these are images from the thermal system when moving around in this smoke-filled training facility. So you can see that we see quite a lot in the thermal camera images. Quite a lot of contrast is visible, a lot of things you can keep track of to keep track of your motion, basically. The visual system in the same environment didn't see anything, partly because it was very dark in there, of course, but also because of all the smoke. And here is the link to a demonstration video from the walk in the smoke-filled environment, where you can see how we track landmarks, what we see, how we create the map, and so on. And if you look at the YouTube channel, which this video belongs to, you also get links to all our other demonstration videos. And that channel link is also available in the text document on the left-hand side of your screen. So that concludes my part of the presentation. So back to you, Alan.
Thanks very much, Joakim. Well, as Joakim explained, he is working on a research and development project. So while this kind of technology, this kind of indoor vision in smoke and mapping may be coming your way sometime soon, or something similar may be available, it's not available now. By contrast, our next speaker, Derrick from Laser Technology, is going to tell you about tools you can use right now, today. Derrick, go ahead, please.
Well, thank you, Alan. It's a pleasure to be part of the Market Insight with GPS World today. I'm going to go ahead and talk about laser rangefinders incorporating with GPS, apps, your own device, just how you can make that workflow a little easier where you might not be able to get that signal that we were talking about, get that GPS signal or the GNSS signal. Just a little bit about laser technology. We've been in business 30 years. Actually, this year is our 30th year in business. We manufacture, design, and distribute laser rangefinders that measure distances and also speed. We specialize in tilt and compass sensors also, just to do different measurements such as heights or spans. Not only hardware that we work on, we also work on software solution or apps because you have to collect that data. Just a couple of firsts with laser technology. We worked with NASA for a proximity laser, ship docking. We did that back in 1991. We worked with recreational rangefinders, a company called Bushnell, back in 1994. We've designed the first golf and hunting laser rangefinder with Bushnell, and we still do that today. We also designed a criterion laser that measured distances, angles, and had azimuth, and we incorporated that with a GPS unit back in 1992, kind of becoming the first reflectorless handheld total station. Talk about a little bit about the sensor technology and the measurement solutions that you get from our laser rangefinders. Our laser rangefinder here, the TruPulse, when it's fired, laser pulses are transmitted in a narrow beam to the object. The unit will accurately measure the time it takes those laser pulses to travel to and from the object, and also known as time of flight. With this information, the TruPulse calculates the distance to the target. So we built in the range or distance sensor in the TruPulse models. The laser sensor we specialize is pulse technology, also known as reflectorless. Our units can acquire measurement to almost any type of target up to 3,000 feet without a reflector. No need to have a second person with a prism pole. If you need farther measurements, you can use a prism or a reflector to get out to about 6,000 feet. Our lasers do not have a laser pointer, and you cannot see the laser pulses being emitted. The laser energy is a class 1 eye safe, so it will not cause any eye damage. Other sensors that we've developed, I talked about, are the accelerometer sensor. Basically, we use this to measure or know the tilt of the unit itself. So using the accelerometer, knowing the forces of gravity, we know where the unit is tilt plus or minus 90 degrees. And another sensor we've developed, a compass sensor. We use a compass sensor in our laser rangefinders to measure magnetic north, so we know what azimuth direction we can get. With the TruVector compass technology we have, the engineers designed, there are no pitch and roll limitations with the unit, and it will always maintain that plus or minus 1 degree accuracy. Another thing about our TruVector compass technology is we notify you if the compass is not accurate. We try to maintain that plus or minus 1 degree, and we give you an indicator that it needs to have a field calibration done. So with all these different sensors, what do we do with it? First thing we do is measure distances. So with the laser sensor, distance sensor, we get that slope distance value. With the tilt sensor, accelerometer sensor, we get that inclination value. And with those two different values, we're able to calculate the VD, vertical distance, and also the horizontal distance, all on board at one shot. When we incorporate that compass sensor, now we measure an azimuth. Now we've got that slope distance to the object. With inclination, we know the tilt inclination to the object. And now with the compass sensor, we know the azimuth direction. So now we have everything built into one, so now I know I can get the XYZ measurements from one location. And all this is done for doing a laser GPS offset. This is kind of what we incorporated into this world. You occupy a GPS coordinate in one position. You take a measurement to a remote object, and with some software, it's going to calculate that remote GPS coordinate. So you're standing in one location, take a measurement to the target, and with the values the laser gives you, the software will calculate that remote GPS coordinate. So this all relates into mobile mapping, what we need to do and how we need to do it in the field. So what is it in for me? Or how do I collect all this data? The biggest thing I want to talk about, I'm going to talk about a few devices here, basically on Android. It's kind of like bring your own device that you can have and use the internal GPS device on smart devices. Use some of these apps we have developed here. Excuse me. PocketGIS is an app that one of our partners developed over in the UK. It's basically just to collect a mobile data collection app. You can use the internal GPS of the smart device, and it also comes with that laser tool built in. So it does have that laser offset that I'll be talking about already built in this app. Another app a partner developed for us, or developed for them, is called GeoJot Plus. This is where you can take pictures with phones, use your Android phone, and also integrate that with laser and the internal GPS device on the phone. What you want to do this for, you want to document the evidence with the photos, do proof of performance, or do some site assessments. An app that we developed, Laser Technologies designed, is called MapSmart. We designed kind of a GIS solution for the non-surveyor. Just pretty simple unit to capture the laser data coming out of the TruPulse line. I capture points, lines, polygons, etc. Another feature in this MapSmart software is that we can do actually volume. If you have a stockpile of inventory that needs to be done, and you want to know the volume of that, you can use our laser rangefinder in this app to calculate that. This app that we're coming out with here shortly also uses the internal GPS device on smart devices. So how does it relate to the GPS world and geospatial? Especially with all those apps I was talking about, they can use an external GNSS receiver. You want to increase that accuracy of your smart device. We all know smart devices gives us so much accuracy with the internal GPS, but for better positioning, what we need to have is an external GNSS receiver. Using these external GPS or GNSS receivers, you can connect via Bluetooth instead of using the GPS on your smart device. And there are a lot of different receivers on the market right now. You can see here, there are a few of these external receivers that those apps I just talked about do connect with. So how does it relate to you? How does this go into my workflow? What's in it for me, right? We're all selfish people. So the biggest thing we would do is increase your workflow. We want to talk about what is an offset. There's different offsets we want to do here. The laser offset I talked about, you get your GPS position, use the laser rangefinder to measure the distances, and the GIS software, those apps, will calculate that remote position. So there's some things you need to take into consideration when you're using laser offsets. The first is the accuracy tolerances. Your accuracy, your distance, inclination, and your compass. You want to take a look at that to make sure if you're using external receivers and you want a very accurate laser device to get that accurate offset position. You want to look at the cost of ownership or use what you already have. Also the training time. How long does it take to train on laser devices, etc. Our lasers in these apps we were talking about, you can get running up within about a half a day or even quicker just by reviewing material that we have, the training material. Other things you want to consider when you're doing laser offsets is portability and size. Don't want to be lugging around a lot of devices out in the field. We're trying to eliminate all the devices that we have out there or make them smaller and easier. So you want to look at portability and size of laser rangefinders or the user experience. With our TruPulse line, you want to be able to, it's got a 7 times magnification so you can actually see the target that you're aiming at. You want to make sure that user experience is easy. And also we talked about that field calibration. We watch out to make sure that compass is accurate so your offset is also accurate. As you can do field calibrations right up, and they take about 30 seconds to do a compass calibration. And it comes to that workflow. How am I making it easier? Do I want to stand in every position or do I want to stand in one location and take offset measurements with the laser rangefinder. So with these apps and having a laser offset function built in, that workflow efficiency can be much quicker and easier. What are the different applications? Again, how is it used in the field? When you need to be safe. You got to look at, I call this the Doberman factor. I don't want to occupy the point across the fence with my GPS device. Or I can't because there's too many cars rolling around in the middle of the road. Or when you need to save time. I don't want to occupy every point. I can stand in one location, take multiple offsets, and capture the offset at that time. Or when GPS or GNSS is blocked. Different areas, the canopies, urban canyons might not be as accurate as you need, or what you can use is the laser rangefinder to do those offset functions. So some of the benefits that we're looking at is work with what you already know, or bring your own device. You already have that. You can download apps that we talked about. There are other apps and other solutions out in the world, but I was just showing a few of them that have that laser interface built in. You can also collect height measurements or spans. It's not just all about the offset measurement. You also want to utilize heights, spans. You can capture that information. And the other thing we want to do is map quicker, smarter, move less, and experience a quick ROI. And back to you, Alan.
All right. Thanks very much, Derrick. We're going to hear next from Eric Gackstetter. Before I turn the floor over to Eric, I want to remind everyone that if you want to review any of this information, or if you want to share it with any of your colleagues, within a day or two, certainly by next Monday, this webinar will be posted to our website. You can download the entire audio file. You can download all the slides. All the information is easily reviewable, easily shareable, and we hope that you will. I'll return after Eric's talk to field some of your questions and throw them at the presenters. Right now, let's hear from Eric Gackstetter, Contributing Editor, GPS World and Geospatial Solutions.
Yeah, thanks, Alan. So we're going to talk a little bit about different kinds of sensors along with GNSS. But just by way of background, I mean, I'm a GNSS person. I've been working with the technology for a number of years, 25 years about. And sort of the neat part about it is that GNSS, of all these sensors that we're talking about, is the only one that can provide a centimeter accurate position anywhere in the world. So it's this global latitude, longitude reference system. And so it makes it unique, and so it really makes it the core technology for positioning. So that's the neat part about it. But so the drawback is that GPS or GNSS doesn't work everywhere, and it doesn't necessarily collect all the data that you want it to do. GNSS is purely a positioning technology. So when we talk about wanting to have a digital photo, for example, of a valve, that might provide useful info about that valve, the condition of the valve, or even help on the location too. Attaching the GNSS coordinates provides spatial awareness of the valve or streets or pipes or sidewalks or whatever. But that's just sort of the core. And in most situations now, people want to collect more feature-rich data, not just the lat-long coordinate. So anyway, so in the past 10 years, it's been interesting. Other sensors have really been developed that make for interesting applications, and a big driver behind that is mobile devices. And I'm talking about smartphones and tablets and so on. But these devices have really driven the R&D effort for small sensors. I mean, you look today at the type of camera that you get in your smartphone is just amazing. You get 8 or 10 megapixel cameras in your smartphone, and your smartphones also have accelerometers and inclinometers and compasses and barometers, in addition to GNSS receivers inside them too. So this whole mobile device explosion has caused just a tremendous amount of work to be put into cost down and size down of these different sensors. And then even further, just in the past 5 years or so, the explosion of UAVs, of drones on the market has further pushed that R&D effort to produce more high-resolution mapping sensors, such as even cameras, for example. You can get a 24 or even I think 48 megapixel camera on a UAV that just takes tremendous imagery, highly detailed imagery. There's LiDAR sensors, thermal sensors that measure heat, NDVI sensors, and so on. And so there are some, and also there's some navigation sensors, as I mentioned before, like accelerometers, but there's initial measurement units that go along with GNSS to help GNSS in environments where it's not built. I mean, a problem with GNSS, or I guess a weakness of it, is it works great out in the parking lot of a shopping mall, but once you step inside the shopping mall, your positioning doesn't work very well. And so there's been a lot of development, or there is being a lot of development put into developing high accuracy inertial measurement units that will allow you to navigate indoors. And there's lots of technologies being tried and developed, from beacons inside shopping malls to other types of sensors to help that kind of navigation. So you see in this particular slide, I've got the name of this sensor technology. Then on the right, I typed in either navigation or data in terms of data collection. So IMUs are purely a navigation type of augmenting technology, as well as accelerometers and inclinometers. Those help us navigate around, and certainly in the future you're going to see more sensor fusion with GNSS and those technologies to help us navigate in difficult areas. I mean, from a mapping standpoint, we personally, I run into situations many times where if you're underneath trees, tree canopy, or next to buildings, or in corporate parks and that sort of area where there's lots of obstructions, GPS can start to fall apart pretty quick, especially high precision GPS like RTK or submeter. And these IMUs and accelerometers and so on, these types of sensor technologies are being pushed further and further, and I think will become, and in fact I know they'll become better and better and highly fused with GPS, so we'll be able to navigate accurately within more areas. And then you see down towards the bottom of this slide, or the mid and the bottom, is these are nav and data. For example, GNSS is a navigation tool, but it's also a data collection tool because you want to record coordinate. And then laser rangefinders, of course, we talk about it a lot, and Derrick talked about that as being a data collection tool. But if you can imagine, it also can be a helpful navigation tool also. If you have a number of laser rangefinder sensors on a vehicle, or such as a UAV or even a terrestrial vehicle like an automobile, and they're constantly sensing things around them, it can help actually navigate and with collision avoidance and that sort of thing. And then, of course, 3D scanners. The first speaker spoke about those. Is when you go indoors, if you use a high-speed 3D scanner to even navigate around a room or interior of a building, and those are valuable for navigating and for collecting data. You see 3D scanners even featured on television, where CSI crime investigation will go and scan a crime scene to create a 3D point cloud of the entire scene. And of course, there's cameras. That was sort of the low-hanging fruit for the sensor industry in terms of UAVs and smartphones, is higher and higher quality cameras. And like I said, it's pretty amazing to look at the small size of the camera on your smartphone and the kind of imagery it can record. It's just absolutely amazing. And then there's LiDAR sensors, which are becoming smaller and cheaper, and I think I have a slide on those. And also thermal sensors, which are really interesting. Those are sort of, to me, they're sort of following the LiDAR path. People are starting to understand the value of thermal sensors. So this next screen, I discussed this a little bit, and here's just some examples of them. So there's the sensor fusion. These navigation sensors, and for example, there's a LiDAR sensor down at the bottom. That's a new Velodyne LiDAR sensor, one of the really expensive kinds. Those can be helpful in navigation. There's a FLIR thermal sensor in the upper right-hand corner, and then there's a super high-res RGB camera on the lower right. But the point is that these sensors are all becoming smaller and less expensive and even interchangeable. I was just on a conversation earlier this morning. We were talking about UAVs on in this conference call, and one of the big subjects with the UAV was how can we plug and play different sensors on the UAV. For example, if one of the missions of the UAV is to collect ortho photos, aerial photography, you plug in a 24 megapixel camera on the gimbal of the UAV. And then if you're interested in collecting highly accurate elevation data or terrain modeling, you plug in a LiDAR sensor on UAV. And then if you're interested in detecting wildlife, certain kinds of wildlife or other hot spots, you can connect a thermal sensor like a FLIR sensor on the UAV. So the UAV and mobile device market are driving the cost of these and the size of these sensors down, and it becomes a really interesting way to collect a lot of feature-rich data with a lot of flexibility. And this is just a couple of examples I wanted to show you. So this was a Google Earth image of an area that I shot with the UAV. So this is the Google Earth version of the image, and then the next slide, this is the image that I flew with my UAV. This is with a 12 megapixel camera at about 200 feet above ground level, and I'll just flip back to the Google Earth slide. Google Earth is actually not bad, but you look at the detail and the resolution of a 12 megapixel camera at 200 feet. I mean, I can't zoom in here on this particular software, but it really shows you how detailed this is. This imagery is about 2 centimeter pixel resolution, so each pixel was about 2 centimeters wide. If you look close, you can see me right in the middle of the screen. I've got a blue jacket on, and I'm in a couple of the pictures here because this was an ortho mosaic, or this is a mosaic of many different photos combined to produce one ortho photo. And so I was in a couple of shots. I was moving around. And here's another example of a sensor, and this is really fascinating technology. This was another one done with a UAV. This is a mosaic of photos taken from a UAV at about 200 feet above ground level. And what's fascinating about this is that, there's a term called FODAR. You've heard of LiDAR probably, which you can get, which is the laser sensor that shoots out tons of different beams and can map terrain. FODAR is sort of a similar type of technology. You fly from a UAV or a manned aircraft, and you just fly at a really heavy overlap. In this case, it was 80 or 90%. And then from those, you can create 3D models. And this actual 3D model was taken from just a series of photos. And so there's some fairly interesting technology out there. I'm going to skip back to that slide. You can get even free software on the market. I think Autodesk has got a piece of software, and there's some others where you can take photos with your camera, your smartphone camera, and take a 360-degree photos around a person even, or an object, and then run it through this Autodesk software, and it will create a 3D model of that person. And this technology is available, and that's free, and this technology is available today. And there's similar things in UAV processing software that allow you to generate some really interesting 3D models of almost anything: terrain, structures, trees. It's just a matter of how much data you want to collect. Because, of course, the more data you have, the better the representation of the 3D model is going to be. And this here is an example of a heat map, and this is those lines there are contour lines, elevation contours that were generated from a UAV ortho photo flight. So this was taken again at about 200 feet above ground level. This is the size of this property is about 200 acres. Just by way of background, it took about 3 hours to fly it and generated about 2,000 images. And then these images were mosaicked together using image processing software. And then a digital terrain model and surface model were built from that. And these elevation contour lines were produced. And these are 1-foot contour lines. And sort of the test here, this is a project that I did for my own education, was to see how accurate this really inexpensive UAV could collect this type of data, and it was actually pretty amazing. We set out some ground control points and then also took some test shots on the ground with RTK, and then we generated contours using the ground control points and then tested the elevation accuracy against RTK test points, and they were spot on all over. In fact, I probably could have generated 6-inch contour elevation contours, and I think they would have been pretty close also. So just anyway, an example of different kinds of sensors, and if you can imagine, it's not just the UAV airborne sensors. You can put these sensors on ground vehicles also, terrestrial vehicles, and they've been, folks have been doing this for a lot of years. You look at Google Street View, you look at those vehicles, and they're just equipped with all kinds of scanning and GPS technology. They're almost the epitome of sensor fusion. They're just in this car, whereas in the future, they're going to be much more refined and smaller and cheaper and more affordable for the regular consumer. So, Alan, I think we've got, 9 minutes or so? I don't know how many questions. I haven't been keeping track or watching questions. Do we have any questions we'd like to address?
We have several questions, some pre-submitted and some have come in during the webinar, and we actually have a little bit more than 9 minutes. We can easily go past the top of the hour. We've got good attendance sticking with us. Derrick, I want to ask you one question that just came in from one of the listeners who says, now I've lost my question. Just a second here. Here we go. The listener wants to know, I'm interested in sub-decimeter accuracy in GNSS denied environment and stakeout to known points. Sounds to me like your equipment is going to handle that, but why don't you tell us a little bit more in detail?
Like I described, utilizes some of the apps or even some of the different third-party software solutions that you can utilize an external GNSS receiver that will increase your accuracy. And then from there, we can use our laser rangefinders to get that from that one point and do that offset function, how to do more stakeouts to other known points. You can do backsite also with the software solution that is, if it has that routine built in, could be in some of those apps or third-party solutions. Do you have anything to add on that, Eric?
Eric may not.
Oops, I was on mute. Sorry about that. Yep. So, so in the outdoor environment, and certainly laser rangefinders are a very useful tool. I've done a lot of mapping on golf courses, and if you can imagine, your choices when you're mapping trees on a golf course is that you can A, go try to occupy each tree, or B, even a better solution. Occupying each tree, A, takes time, and B, you submit yourself to a obstructed environment, because under tree canopy, of course, its accuracy is going to degrade. So in that case, I would stand out in the middle of the fairway, take one GPS position at the decimeter level, and then shoot each tree with the laser rangefinder. Indoors is a bit tougher. I mean, I'm still waiting for the decimeter solution indoors, and maybe it's reliably there. It's a combination of certainly of imaging sensors, and you could. I just don't know how to maintain decimeter accuracy absolute-wise. I think precision you could, but I'm not sure absolute-wise.
Yeah, I agree. It would be very difficult to maintain it if you don't reobserve some kind of references. I mean, for specific patterns of moving around indoors, you could recognize that I've been here before and so choose a loop, and that way you could keep track of it, but not for general motion where you don't reobserve anything.
But I tell you what, the first person who's able to do that is going to be a really busy person.
Yeah, I guess so. But in principle,
when you're talking about things that work with smartphones, the question of versions or editions or whatever you call them always comes up, legacy equipment and so forth. One listener wants to know, will the products demonstrated work with older equipment, for example, older phones, both iPhone and Android? How about that, Derrick?
Yeah, Alan. With our laser rangefinders, what we do, we interface with different operating systems, older operating systems with different devices, such as Windows mobile devices and Android. All of our lasers actually interface with Windows mobile and also Android. And so you might have some equipment already, that older versions of Android that could run an app that our laser rangefinders would interface with. As far as iOS, we do have a couple laser rangefinders that interface with that. They had to be, of course, Apple approved with the Bluetooth module, which is sometimes fun. But we do have a couple laser rangefinders that do interface with the iOS operating systems or smart devices.
Terrific, terrific. Sounds like you got a solution for almost everyone. One person wants to know if we've been talking about how you can augment the positioning of GNSS with various devices. How about actually improving or increasing the accuracy of handheld GPS or Android apps for use in mapping? How is that done?
This is Derrick. Go ahead.
Go ahead. Okay. I would say that the main idea behind augmenting the performance would be to include data from some other sensor as well. And I think that Google is making this much easier with the next version of the Android operating system, because it's said to provide apps with not raw GNSS data, but at least pseudo ranges to satellites. And then when you don't just get the final position estimate from the GNSS module in the phone, but you get this slightly raw data, it's much easier to combine that with data from accelerometers and gyroscopes in the phone, and possibly even the camera in the phone, doing something similar to what I was talking about. So hopefully we will see a lot of apps where some kind of sensor fusion is performed to increase the accuracy, at least in environments where GPS or GNSS outages or quality reductions are temporary.
Yes, that's an important development.
Alan, I was going to say, Alan, Todd Humphreys down at University of Texas at Austin, he published a paper, I think in GPS World not long ago, about taking photos, images, and then being able to position from those via crowdsourcing. But you're right, he still needs a reference of some sort, and so that's still a challenge there. But I think one of his premises is that there's so many photos being taken out there that there's location references everywhere, and that if you can pick one of those up with your photos, you'd be able to position yourself fairly accurately. It's an interesting concept, certainly.
Derrick, a final word on that question before we move to another one?
Just kind of what we talked about during the slides there is if you're using your smart device and you use those external sensors or receivers to increase that accuracy, it all depends on the app or that can talk to the external GNSS receivers that are more accurate than your smart device itself.
Okay, and what Joakim referred to the new thing from Google. If you in the audience are not aware of this, we have a story on our website. It's an important announcement from Google about making the raw data available. If you go on gpsworld.com and in the search function up top, just type Google, you'll quickly get the story. We got it straight from Steve Malkos at Google, who's been very instrumental in developing this exciting new capability or new offering of the capability that's there, making it available. We've got a question now from a listener who has a fairly specific or particular use. He writes, I would like to collect data inside of manholes. Derrick, I imagine you probably have something that'll fit this person's need.
Well, it does depend on taking measurements down a manhole. If we're just talking about taking the distance, if you just want the distance down, of the manhole itself, you'd be able to do that with one of our laser rangefinders, just to get the distance. If you're measuring, if you need to position things going down the manhole, that's a little more difficult. But if it's just down the distance down the manhole, just to get the opposite height or the depth, you can do that with one of our laser rangefinders. But to navigate also down and in is also very difficult.
Down and in is difficult. Straight down is
straight down. Like if I needed to map, take a position on the street level, and then take some measurements like traverse down the manhole, and then continually traverse within the pipes, that is a little more difficult to do. But if you just need the depth of the manhole, you can do that from with one of our laser rangefinders.
All right. We're at the top of the hour. We're a little past, but I'm going to take one or perhaps two more questions here. One person would like to know, and this is sort of I won't characterize the question. I'll just ask it. With what used to be complex tools getting cheaper and more distributed and more untrained people using them, how can the quality of measurements be inherently guaranteed? Now, sticking the word inherently in there is perhaps an unfair qualifier, but how can we address the quality of data when the tools are being more and more widely used by, let's say, less and less trained people? Anybody want to venture an opinion on that?
Sure. Yeah. So this is Derrick. So what we're seeing more and more, especially in the GNSS industry, is that receivers are outputting RAIM type of messaging, receiver autonomous integrity monitoring. So it gives you some level of estimation of accuracy. And I think that's increasingly important, and we're starting to see this more and more in high-precision receivers. In fact, almost all high-precision receivers output this kind of messaging. Not all app software consume it, which is a problem, but it's being output by the receivers. Now, when you get into the consumer-level receivers, virtually none of them really are outputting that type of messaging. And a lot of them actually don't, for the lack of a better phrase, don't care about accuracy. I mean, as long as they can get the user, let's say of a smartphone, from the house to a soccer field, that's good enough accuracy for them. But I think as accuracy in smartphones, as we see with Google is possible, this new Google release, as accuracy within smartphones becomes better and better, the questioner is correct in that, how do you determine the quality level of that data? And I think some kind of estimation of precision has to be output and has to be displayed by the app software.
All right. Thanks very much. I'm going to draw to a close here. We have a couple more questions that I will make available to our speakers, and we'll see if we collect written answers from them over the next week or so and make them available. Meanwhile, I want to thank, again, our sponsor, Laser Technology, for enabling us to bring you this webinar on sensors to augment and complement GNSS. I'd like to thank our three speakers, Joakim Rydell from the Swedish Defense Research Agency, Derrick Reish from Laser Technology, and Eric Gackstadter from GPS World and Geospatial Solutions. Thanks to you, our listeners, for tuning in. I think we'll have information on our next webinar coming up shortly. Stay tuned to the GPS World website and the various newsletters that you may subscribe to. Once again, on behalf of all of our speakers, thank you for attending and have a great day.
Like Alan said, thanks for attending our webinar. Just so you're aware, a recording of this webinar will be emailed to you tomorrow and posted to gpsworld.com/webinars. Any upcoming webinars from GPS World also will be posted to that same page. So thanks for attending, and we hope you'll join us again for a webinar in August. Thanks.